All right, let us look at this fascinating problem that is taught in many classes worldwide. A human is standing on the surface of the Earth near a gravitational tunnel and jumps into the tunnel and falls down here, also over to the other side. But the question is, at the fall, which velocity will this guy have? And in order to solve this problem, one simple way is to use Newton's shell theorem, which states that suppose we have a massive spherical shell and you would like to know the force for a particle inside the shell, the blue one here. And when you add all the interactions, the gravitational interactions between the particle and the small mass elements here, this we can do by integrating. That's the same thing as summing all the small infinitesimal mass elements. And what we find out is that the total force acting on the particle equals 0. So the particle is not feeling any force inside the shell, no matter where the particle is placed. The obvious symmetrical thing is if you place it in the center, of course, by symmetry, there is no force. All forces will cancel. So if we look at this solid Earth problem, it means that if you're here, you can think about shells around above you, several shells, and none of them is giving any force that you can feel, at least as a particle. So what it means is you don't have to consider all the mass above you when you fall here. So only the spherical mass beneath you is of interest for calculating the forces. And in this particular problem, I would like to know the velocity here. So the radius of the Earth is capital R, but when you're here somewhere, the distance to the center is just R, like shown in this picture here. And we need to figure out what is the forces now. If only the mass here matters and everything above, all the shells above you, doesn't matter. Well, it is a trivial thing, actually. According to Newton's law of physics, we have, let's write it like this, the gravitational law, G, and the mass of the sphere having radius R, and your mass, the particle mass here, divided by R square. So that is the force. And this we usually write like this, M and the G field, and it depends on R. In the case where we are standing at the surface of the Earth, there is another force, and that is then GMM over R square. And here the mass is of the Earth, the total mass, and here is again the particle mass. And this is what we usually write like this, M g, where g usually is said in SI units 9.81 meter per second squared. All right. So we need to find out here something. If we continue here, m equal density times the volume of the Earth. On the other hand, mr has the same density but a different volume. Yeah. So m divided by mr equal v divided by vr, which this equals r3 divided by r3. So let's see here if we know something more. So f r divided by f that's m r divided by r squared and f and r squared over m. And mr above m, that is r cubed, and then okay, wrong. R divided by capital, right? If this here equals that, yeah, so it must be the opposite. And then you have r squared like that, so that's equal r divided by capital R. Then we know that. So then we can write it like this. Fr equal f r divided by capital R, and this is f is simply mg divided by Earth radius times r. Okay, and let's suppose mg over Earth radius is a constant k. So this is the expression we have. This is exactly what we wanted to know here. What is the force for radius r? And this is the thing we have here. So, and now we would like to know the velocity. So we know the force for any r, from r equals 0 here, all the way here. We know the force all the time, and also here, if you like to know that. But the question is, what is the velocity here? So a neat trick here, sure, I could say this is just a spring equation, right? Something like that. But actually, if you look at the force here, if you think about that we have a coordinate system here in the center, and axis r, like that. Then we realize that the force is always in the opposite direction, right? Wherever you are. So there must be a sign here that we change. Minus. The force in the r direction is in the other way. All right, that's what it must be. So this looks like the spring equation. What we get usually, see, something like this, kx, it's exactly the same. And what we can do to quickly find the velocity is using conservation of energy. So what we need to do then, what is the potential? Well, it is this one, k r squared. Why? Because the force equal minus du, the derivative. So here is the potential energy, and we also have kinetic energy. So what we have is this, 1/2 mv squared plus 1/2 k r squared. And the energy from the start, then we start with velocity 0, and we start at the Earth radius r equal Earth radius capital R. So then we have 0 plus 1/2 k r squared equal, and in the center of the Earth, when we are there, then r equals 0, but we do have kinetic energy. So then we have 1/2 mv squared plus 0. And this, then we can solve the problem. V equal k over m r, like that. And k is mg over r, so this is g over r times, so this equals gr. And that corresponds to about 7 kilometers per second, the center of the Earth. Thank you very much. See you next time. Bye bye.